Hi everyone, welcome back. In this segment, we are continuing on solving examples using integration by parts. And in the first segment, we had derived a formula and we've been using it. So for problems that can be written of the form integral of u dv, the formula was uv minus integral of v du. So here's another example where we're going to integrate x squared times cosine x. And this is an example to show you that you can use integration by parts repeatedly. So for example, based on what we learned last time, you can let u be x squared, right? Because its derivative will keep getting easier and easier over time as you differentiate it. So for example, let u be x squared, its derivative will be 2x. And let dv be cosine x dx. So there you anti-differentiate, you're going to get positive sine x. Okay. And then we learned that to use this formula, you're going to do u times v, so u times sine, so in this case x squared times sine x, minus integral of v du, which is minus integral of 2x times sine x. So at this point, you can factor the 2 outside. Notice what you're going to have there. You're going to have the integral of x times sine x. And that is very much similar to the problem from the last segment, right? So once again, it's a question that can be solved with integration by parts. So if you take the 2 outside, you can even keep the 2 in there and let u be 2x and dv be sine x dx. That would be another way to go about it. So in this case, I have let u be 2x. So dv is 2 dx. And let dv, so du is 2 dx, and let dv be equal to sine x dx. So there we need to anti-differentiate, and the integral or the antiderivative of sine x is negative cosine x. Okay, so once again, we're going to apply integration by parts, but don't forget this first piece has to still be there. So copy that over. So that's just x squared times sine x. So that part is being copied over, minus sine is being copied over. Now for this integral, again, we're going to use the formula uv minus integral v du. So open a parenthesis there, and or bracket, whatever you want is. So uv, so 2x times negative cosine x, so that's negative 2x cosine x, minus the integral of, so originally there's a minus there, minus the integral of v du. But notice that that in itself is bringing another negative sign, right? So that's why I can make this a plus right now. So minus came from the formula, another minus came from here, multiplying gets it to plus, minus integral of v du, integral of this times that. And when you take the 2 outside, you're going to be left with integral of cosine x. So you can take the 2 outside, the negatives turn into positive. I'm going to just get rid of that. And what do we know about integral of cosine? That it is sine, right? So this integral can be handled very easily. So in 2 steps, we are able to solve the original question. And don't forget to distribute this negative sign that was sitting on the outside. That'll make this one a positive and that one a negative. So I distribute my sign, making it negative, then integrate integral of cosine as sine, and that is our final answer. Don't forget the plus c at the end. There's a negative mainly because there was a negative already, right? Other than that, the integral of cosine is indeed positive sine x. And notice the first 2 terms have been copied over exactly. In the last step, all I did was take this integral of cosine x. So in this example, we saw, yes, you can apply integration by parts repeatedly. Like what if this had been x cubed cosine x? Yes, it can still be done. It's just going to take a long time. And mathematicians realize there is a simple way to do these kinds of problems, and that is known as tabular integration method. And with tabular integration, what you do is you create 3 columns. One column will be u and its derivatives. One column will be v and its antiderivatives. Another column will be alternating in sign, plus minus, plus minus. Okay, so remember that our u was x squared, and out of dv, we got v equals sine x. So to do the tabular integration, you have to go back to the original assignment of u and dv. So you still have to do this part exactly as it is. And from here, you're going to extract what is u and what is v. Okay, so this first step, though, you still have to write it out. U, du, dv, v, and everything. Okay, but now that we know u is x squared and v is sine x, we can put them in here. So u is x squared, v is sine x. Okay, so in the first column, you keep differentiating. Okay, derivative of x squared is 2x. Derivative of 2x is 2. Derivative of 2 is 0. Next, keep taking antiderivative. So the antiderivative of sine is negative cosine. Antiderivative of cosine is sine, but with a negative sign, it'll be negative sine. So an antiderivative of cosine, negative cosine turns out to be negative sine. Okay, so let's do it one more time. As a matter of fact, we don't even have to do it because once you get a 0 here, you don't need to know anything across from that because it'll get multiplied, it'll disappear, so you don't even have to write that one down. But if you had to, antiderivative of sine is negative cosine times the negative is positive cosine. So now what you do is, don't forget the plus minus alternating signs here. You're going to multiply them across. So positive x squared sine x, we write it down. That's going to be our first term. Then negative 2x times negative cosine x, that multiplies to positive 2x cosine x, you get the second term. Then positive 2 times negative sine x, that's altogether negative 2 sine x. And then here you get nothing, 0. So just you add then the plus c at the end. Check that with our earlier answer, and you'll see it's exactly the same. The answer up there, you're going to see is exactly the same as answer down here. So that example shows you how to handle a situation where you need to apply integration by parts formula repeatedly. You can use either one of these in my view. I personally think this one is very easy to forget, even though this is a little bit longer. Up to second degree, I would still go with this. If it's higher than second degree, I would say, okay, let's dust that. What was that technique again with tabular integration? I would go and use that one. All right, see you in the next segment where we're going to solve integration by parts examples involving the natural log function.